Hello viewers, you're welcome to ISIFE educational blog, and my name is Uncle P. And if you are new in this channel, you follow, or you like, or you share our videos. And if you have any question, you can go to the comment section and drop your questions. And we are going to be looking at a redox reaction under these objectives of the lesson. We have a meaning of redox, that is definition of redox or reduction oxidation reaction. And then we're going to be looking at the rules of oxidation states, and then thereafter we look at reduction and the oxidation definitions. We have oxidizing, reducing agents, and then you follow the link, and then have some work, past question and answer, nickel as GC, past question, UTME, and then post UTME. Okay, we're going to take it one after the other. Meaning of redox reaction. What is redox reaction? This is a type of chemical reaction in which oxidation and reduction occur at the same time, or occur in the same reaction. So I can easily say that redox. Okay, briefly we say that redox is a type of chemical reaction in which oxidation and reduction occur in the same reaction. So any reaction in which oxidation is going on as well as reduction, that reaction is said to be redox, or is said to be reduction oxidation reaction. That is a short definition of redox. But on the second objective of the lesson, I would like us to look at some of the rules that governs oxidation states of some substance, elements, molecules, and ions. So in our second lesson objective, we're going to look at the rules of oxidation states. One of the rules of oxidation states is that the sum of oxidation number of a neutral atom, molecule, in their uncombined states or compound, in their uncombined states is equal to 0. The sum of oxidation states of a neutral atom or molecule in their uncombined states of 3 states is equal to 0. Take for instance, if you have an atoms such as sodium, potassium, beryllium, carbon, oxygen, carbon, aluminium, etc. These atoms of these elements, as they are neutral, they are not combined, the sum of their oxidation states is all equal to 0. And then if it is molecules, we have 3 aspects of molecules. A molecule can either be diatomic, triatomic, and then polyatomic. So we have some diatomic molecules. We have hydrogen, oxygen, nitrogen, and all of that, bromine, iodine, etc. The sum of the oxidation state, as they are not combined in their molecular state, is also equal to 0. Same thing goes to ozone. A triatomic molecule is also equal to 0. And then some polyatomic like phosphorus and sulfur is also equal to 0. That is the rule of oxidation for a neutral atom or molecule. And then that's rule number 1. Rule number 1. And then the rule number 2, the sum of oxidation state of oxygen, sum of oxidation state of oxygen in each combined state or compound is equal to -2. Is equal to -2. Oxygen is -2 when it is combined with other atoms of elements. But there is an exception to that rule, which is that in peroxide, the oxidation state of oxygen is not -2, but -1. I'll give example to that rule immediately. Example, what if you are asked to calculate oxidation states of oxygen in H2O and H2O2. This is hydrogen peroxide. This is water. This one is having extra oxygen than normal water. That is, ratio of hydrogen to oxygen in water is 2:1. But here is 1:1 or 2:2. So there is an extra oxygen in this compound. So this is called hydrogen peroxide. So if oxygen is -2 here, what is oxygen in peroxide? Let's find out. And then we are going to look at it this way. We have sum of H2O should be equal to 0. I have to be stating this one as well. It's also a rule that the sum of all the atoms of elements in H and O is equal to 0. Same thing as H2O2 is also equal to 0. So here we have that the oxidation state of hydrogen is +1. And how many atoms are there in water there? 2. Sum of the oxidation state of oxygen is the one we are looking for now, which we are going to take it to be what? X. And then therefore, sum of H2O is equal to 0. So if you substitute, we have that 2 atoms of hydrogen multiplied by its oxidation state. Or rather, I'll say plus 1, that is hydrogen multiplied by 2 plus X, that is oxygen, everything should be equal to 0. So this gave me plus 2 plus X equal to 0. So X, this plus 2 here, crossing over the sign of equality here, it becomes -2. In this other case, we have that H is still equals to +1 with 2 atoms there. And then oxygen is unknown, so it's going to be 2x there, 2x there. So therefore, the sum of H2O2 is 0. And thereafter, we have 2 atoms of H multiplied by the oxidation state of H plus 2x equal to 0. Okay, we have here plus 2 plus 2x equals to 0. So therefore, 2x is equals to, this coming over this side is become what? -2. And then x alone is -2 over 2. X is -1. So oxygen has a variable oxidation state of -2 in most of its compound. Virtually all compound of oxygen is -2. Only where it's not -2 is in peroxide, where its oxidation state is -1. That is in peroxide. Okay, that is on that rule number 2. So we look at rule number 3 for hydrogen this time. In the rule number 3, the sum of oxidation states of hydrogen is always +1 in most of its compound, with exception in hydrides, where its oxidation state is -1. Okay, let's look at these examples. Let's look at this case 1. What if we are asked to calculate oxidation number of P, phosphorus, in pH3? What do? First of all, we have that P is what we are looking for, and then H is, since phosphorus is a non-metal, hydrogen will be +1. That's what the rule says, +1 with how many atoms? 3. Are you with me? So in this case, we say therefore sum of pH3 is equal to 0. So P now is X plus 3 multiplied by the oxidation number of hydrogen when it is combined with non-metals like phosphorus. Let everything be equal to 0 here. So we have that x is plus 3 times plus 1 is plus 3 equals to 0. So x is equals to this going over here, it becomes minus 3. Okay. We can look at case 1. And case 2 this time. Case 2, where we can say calculate oxidation number of Al in LiAlH4. You can pause the video and try it. Okay, without wasting time, since lithium belongs to group 1, all the elements in group 1, the oxidation state in their compounds is always plus 1. That is equal to the valence, the outermost share electron, plus 1. And then lithium, aluminium is the one that is unknown in this question. And then remember, hydrogen in this case is not going to be plus 1 as usual, since it is now combined with one of these metals. So it's not going to be plus 1, but minus 1. Always know when hydrogen is plus 1 or minus 1. Very important. So hydrogen has two oxidation states of either plus 1 or minus 1. Plus 1 is when it's combined with metal and non-metals of group 4, group 5, group 6, group 7. So any combined state of hydrogen with this element in this group, hydrogen will always be plus 1 when combined with this group of elements. When combined with metals of group 1 or group 2, probably its oxidation state will be minus 1. Okay, so that's the case here. So we now have that therefore lithium, aluminium, and hydrogen are 4 of it. Everything here is equal to 0. And then if we substitute down, lithium is plus 1, plus aluminium is going to be what? X, plus 4 of H in this question, multiplied by its oxidation state, which is minus 1, not plus 1. So here will be minus 1. Let everything be equal to 0 now. So this is going to be plus 1, plus X. This gives me minus 4 equals to 0. And so X is equals to plus 1 minus 4. Plus 1 minus 4 is minus 3. But when minus 3 crosses over this side, it becomes what? Plus 3. So this is aluminium plus 3. And if you want to know whether you are correct, you have to try to see if you can insert that plus 3 here with plus 1. So this gives me plus 4 now. So that means that since I've gotten this to be plus 3 and then plus 1 is plus 4, and then this, it says this is minus 1 times 4 minus 4. So minus 4 plus 4 gives me 0. So with this can help me to give this name of the compound. The impact name of this compound then now be lithium. Since aluminium in this case is unknown, so it's actually going to come last in the naming of the compound. So this is going to be lithium 4 means tetrahydroaluminate. Actually, what ends it will be 8 since the oxidation state of aluminium is positive, is in positive direction, not aluminium. It will be aluminium if it is uncombined. This is aluminium. But in the case where aluminium has oxidation number of plus 3, it's going to end in aluminate. What is aluminium there? We got plus 3, and then we're going to have it as written as Roman figure 3. So we have lithium tetrahydroaluminate 3 as the impact name of the compound below. So that is on that rule number 3. So always know that in this rule, oxidation number of hydrogen can either be plus 1 or minus 1. In the rule number 4, we have to look at the oxidation state of some of these elements that are in group 1 and group 2. So in rule number 4, the sum of oxidation number of elements, all the elements in group 1, such as lithium, sodium, potassium, rubidium, oxygen, francium. These are elements in group 1. So in any way you see them in their compounds, whenever they are combined, the sum of their oxidation state will always be +1. So please, that is why in that question we just solved now, in rule number 3, why we assign +1 for lithium is because rule number 4 stated that all elements in group 1 will all have oxidation number of what? +1. That is the rule. And that is how they can exist. They occur in these states. They don't have variable oxidation state or multiple oxidation number. That is under rule number 4. All elements in group 1, all the alkaline or all the alkali metals of group 1 of the periodic table has this oxidation state in their compounds. And then in rule number 5, rule number 5 is for group 2. If group 1 in group number 4 has this +1 as the oxidation state in their compound. So it means that all elements in group 2 or all the alkaline earth metals of group 2 in their compounds, they all have oxidation state of +2. We'll take a look at that immediately. So we have the first element in that group, which is beryllium. We also have a magnesium, calcium, strontium, barium, and radon. All the elements, since they are in group 2, they all have oxidation state of +2 in their compounds. That is on that rule. Okay. Rule number 6 is very, very significant as far as redox reaction is involved. It's very, very important. One of the important rules, number 6, which is rule number 6, very important rule. And why is important is because it has to do with charged particle. Then the sum of oxidation states of a charged particle or ion is equal to the charge on the ion. I'll give you an example here. Suppose we look at these various ions and they'll try to know their oxidation number. We'll have OH here minus. Remember the rule number 2 says that oxidation state of oxygen will always be -2 in most of its compound, virtually in all its compound except in peroxide. Then oxidation state of hydrogen is +1. Only exception is in hydride. So if oxygen is -2 and then hydrogen is +1, -2 + 1 will give you -1. So the oxidation state of OH minus here is sum of what it has as a charge, which is -1. And then for this we have CO3 2 minus. The sum of oxidation states is -2. And then for ClO3 minus, the oxidation state here is -1. For SO3 rather, 2 minus is -2. SO4 2 minus is -2. S2O3 2 minus is -2. MnO4 minus is -1. And then Cr2O7 2 minus is -2. Look at it here. And then HCO3 minus is -1. And so on and so forth. I can't list it out. Okay. What if we make out something out of this? Suppose we have a case here. Let me start it at case 1 from this. Supposing you are asked to calculate oxidation state or number of Cl in ClO3 minus. What do we do? Since we are looking for chlorine, let it be X, and then like you know that oxygen is -2. 2. How many atoms of oxygen is there in that compound? Is 3. So we have here, therefore, ClO3 minus. The sum of everything here is equals to minus 1. Minus 1. And then here will be X plus 3 multiplied by minus 2. Everything here is equals to minus 1. And then here will be X 3 times minus 2 is a minus 6 equals to minus 1. So X here is equal to this minus 6 crossing over here. It becomes plus 6 minus 1. X here is equals to plus 5. Okay, make sure it is always positive, not 5, but plus 5. And this will give us an insight on how we can give name to this compound. We can now say, therefore, since chlorine is the unknown element in this compound, unknown species in this compound, so we can give the name as trioxochlorate. Why chlorate is because chlorine is in the positive oxidation number. Chlorates, what is the answer there? 5. So here will be that 5 will be written in Roman figure as V. And since it is charged, we end with ion. Trioxochlorate 5 ion. That is chlorine in this compound. And then you can pause the video and try this. I'm going to give it as case 2. What if in that same rule you're asked to calculate oxidation number of Cr in Cr2O7 2 minus. What do we do? You can pause the video shortly and try and see if you can solve it. And then we look at it. We have that since we are looking for chromium in this compound, chromium here, which is Cr2, will be 2x. And then oxygen here will be minus 2, and there are 7 atoms of oxygen there. Okay. And then we have that the sum of Cr2O7 2 minus is equals to the charge it has. Not equal to 0 this time, but equals to what? Minus 2. So we have here as what? Instead of chromium, we have 2x plus 7 minus 2 equals to minus 2. Okay. So what do we have here now? We have what? 2x plus 7 times minus 2 is what? Minus 14 equals to minus 2. So we have 2x now is equals to this coming over here becomes plus 14 minus 2. 2x is plus 12 plus 12. Then x alone here is plus 12 over 2. X is plus 6. So with this, we can give name to the compound as hepta. Hepta is 7. Hepta oxo. This is not going to be called chromium since its oxidation state is positive. It will go and end in 8, so it will be chromates. How many are there? 2 now, so it will be dichromates. I think 6 should be Vi. And then it's charged, so here will be what? Ion. That is on that. As very simple as possible. So that's how to solve oxidation states if it is ionic. It will be sum total will be the charge on the ion. Like if the charge on this ion is minus 2, so the sum of everything here should be minus 2. That's what the rule says. So if you are solving oxidation number involving ions, that will always be the case. And maybe I'll try one more before I go to the last rule, which is rule number 7. I'll try one more. Or let's give the question immediately. We ask you to calculate oxidation states of Mn. in MnO4 minus. I would like you to try, pause the video and see if you can solve it. And if you do that, try to give the name of the compound. Very simple. Okay, what we do, since you're looking for Mn, we take Mn to be X. And then oxygen to be 4 of its minus oxidation state of oxygen, which is -2. And then what do we do? Sum of MnO4 minus, since it's -1 here, so sum of everything here should be -1. That's what it is. So here will be X sum of plus 4 atom of this -2, everything is -1. So what do you have here? X minus 8 equals to -1. And so X is equals to, here becomes plus 8 minus 1. So X naught is what? Plus 7. So to give name to this compound, that will be tetraoxo, that is manganese. But as far as this compound is concerned, it's not going to be manganese there because it has positive oxidation state. So it will be manganese. Manganese. What you have here is what? VII, that is 7 ion. That is the name of the compound. So you can try as much as possible to rewind the video and see those ions, try to find the unknown, and that is as simple as that. So the last rule will be rule number 7. Rule number 7. In the rule number 7 there, the algebraic sum of oxidation states of all the atoms of elements in a compound is equal to 0. The sum of everything in H, in this compound, sum of H, 2, and O, the sum of all the atoms, hydrogen atom, oxygen atom in this water molecule must be equal to 0. That is rule number 7. That is the last rule. So whenever you see a neutral compound, the sum of everything in the compound is equal to 0. How do we do that? We must first of all know that the oxidation state of hydrogen is +1. So if hydrogen is +1, oxygen is -2. Before these two are combined to form compound, the sum of the charges here will be 0. So since here we +1, here is -2. I don't think it's giving us 0. I don't think it's giving us 0. But if it must give us 0, that means I'm going to import 2 here. So it's going to be here. As simple as that. So that you can have what? +2 here, -2 here now. Here is what? 0. So at the end, that means if these two should multiply this charge to have +2, this two also is going to multiply this H to have H2. As simple as that. So since this is -2, okay, so there is only one charge. Okay, only one charge. So if there is only one charge, what it means is that this charge times 1 is -2 times 1 is -2. So -2 plus 2 is 0. So since there is only one charge here, that means how many oxygen is still remaining here is only 1. But in this case, there are 2 of these. So there is only one of these. So this becomes O. So the sum of everything here is equal to 0. As simple as that. Or you can take it to this angle. Since the valence, the atmospheric electron of oxygen is 6, which is 1, 2, 3, 4, 5, 6. Oxygen cannot actually use this electron here for bonding. These ones are not available for bonding. So if you must use this one for bonding, this one for bonding, okay, and it's forming bond with hydrogen and hydrogen. Yes, oxygen at this point has achieved octet state stability. It's very stable now, having complete valence electron of 8. Each bond here contains 2 electrons, one from oxygen, one from hydrogen. Remember, hydrogen only has 1 electron. So 1 here, 1 here. So here, there are 2 electrons here. Here, there are 2 electrons here. 2. I think total of 8 electrons. So hydrogen has achieved its own. This hydrogen has achieved its own duplet. This two also achieved that. This oxygen has achieved octet as well. So if I want to check everything here to see if the sum of everything here, including the bonds, are 0, what I will just do is simple. Formal charge Fc is equals to valence, number of valence electron minus total number of bond plus electron dots. That's what I will just do. So formal charge here is equals to valence electron of oxygen. Oxygen has 6 valence electrons, 6 atom shell electrons. 6 is it. So 6 minus total number of bonds here, just 1, 2. 2 bonds plus how many dots are here? 1, 2, 3, 4. 4 dots. So we have 2 plus 4 is 6. 6 minus 6 equals to FC. So FC is 0. The sum of everything is 0, just like what we have here. So take note that a neutral compound should have total net charge of 0. That is why if I want to write a formula for maybe sodium, and maybe this group of atom here, you're going to treat it as just 1. Okay, now since rule number 4, which actually say that is for elements in group 1, once they're in their compound, the sum of their oxidation states is +1. So here is +1, here is -2, here should be equal to 0. So what do we do to make sure they're 0? So that means I have to put 2 here. I have to just put 2 here. So now that we have these 2 here, so we have this will give you +2, +2 minus 2 is 0. So this 2 is going to multiply this to have Na2. So here is Cr2O7. So you see that the sum of Na2, Cr2O7 is equal to 0. Very simple. This is +1. +1 times 2 is +2. This is 6. 6 times 2 is 12. All together we have 14. +14. This is -2. -2 times 7 is -14. So sum of -14 plus 14 should be equal to 0. That's what the rule says. Okay, quickly we go to reduction, oxidation, definitions. That is our third lesson objective. Definitions. Several ways oxidation and reduction has been defined. I'll quickly take you on that. Quickly.